Section 3.3, Conditional Probabilities. So our goal here is be able to compute conditional probabilities. The title says it all. And with conditional probabilities, there's a condition that will reduce the amount of outcomes in the sample space before a probability is calculated. Now, for some of these examples I'm going to do here, you're going to be like, well, how do you know that this is true? And maybe you don't, but it's mostly for the purpose of the example to show you the mechanics of how it works. But in some real life situations, maybe you will know that there's something going on that is going to give you a little bit more indication of what type of object or maybe a characteristic of a person that's going to be selected from the population. So for a basic example here, find the probability of rolling a 3 on a die given that the roll was odd. So here's the condition. We're going to assume that the roll was odd. And if we do that, just looking at the sample space, immediately, instead of having 6 numbers total for our total outcomes that would go in the denominator of our probability, knowing that it's odd, this number gets kicked out, this number gets kicked out, and this number gets kicked out. All the evens go away. So now we are looking at a reduced sample space, 3 and 5, and the probability of a 3 given odd can be written as, with the notation, probability of 3, they use a vertical bar for the word given, and then odd would just be 1, because there's 1 3 out of the 3 numbers that are odd. So the biggest thing to take away from this in your conditional probabilities is that it will reduce the amount of outcomes in the sample space before the probability is calculated. That's the biggest thing to take away. That condition is going to limit you in some way from the bigger whole to a smaller part. From the whole sample set down to a smaller part of it before you even calculate the probability. So the official definition is as follows. A conditional probability is the probability that an event will occur if some other condition has already occurred. So the notation, as I already showed earlier, P of A given B, the probability of A given B, and that little vertical bar is given. So how does this work with a two-way table? You might see some of these in the homework, hint, hint. And I'm just going to fill in the totals here for the rows and the columns and the overall total. Not that we'll need these things necessarily, but just get them in there. And if we're looking only at people who are over 35, what is the probability that they like mild sauce? So looking only at those people who are over 35, they're giving you the condition right up front. So I'm just going to go up here and just focus on those that are over 35. Everything else, get it out of there. Once you're given a condition, everything else that doesn't fit that condition goes away. So what's the probability they like mild sauce? So the probability of mild, given that they are over 35, well, in this case, there are 39 people who are over 35. We don't even care about the ones who are less than or equal to 35 now, so that number 40 there, that goes away. The total 79 gets reduced because we have a specific condition that's limiting our sample space. And then likes the mild sauce, that would be 22 of those 39. And that would be your answer. That's it. So, these are a lot like other probabilities, except you always remember the condition is going to limit your sample space in some way. So the conditional probability concept also applies to situations where 2 events are dependent, i.e. not independent. And if you remember, independent is when one thing doesn't affect the other. When we were looking at that probability of A and B, you would just multiply the probability of A times the probability of B if they were independent. Well, here, when they're dependent, that means that something did change from the first to the second if you're running things in a row. And an example of this would be 2 cards are drawn without replacement. So when you pick up the card, you look at it, you don't put it back in the deck and reshuffle for your second draw. You pick it up, you look at it, and set it to the side. So when you draw without replacement, you're actually changing the number of cards that are left in the deck. That's going to change your denominator of your probability. That's going to mean that you're looking at a dependent scenario. Things are changing. The card you drew on the first one is going to affect what happens next. So that's a dependent situation. And without replacement is your classic indication that you are looking at dependent. So 2 cards drawn without replacement from the standard deck. What's the probability that both cards are hearts? So what we're looking for here is the probability of a heart, or I should say 2 hearts drawn without replacement. On first. And actually, don't even need to say that. We're not drawing after the second. So probability of 2 hearts drawn without replacement. So what we're going to do here is we're going to say, okay, well, the first heart, no issues there. Right? You draw the first heart, nothing's happening. And then we do multiply. This is still kind of an and situation. We want a heart and then another heart. However, without replacement, we have a given condition that we have to worry about. So the probability of the second heart is now going to depend on this given condition that the first one was a heart. And you're always kind of, with these, you're like, well, what if the first one wasn't a heart? And in probabilities, you don't worry about that. You're kind of an optimist. When you're doing these things, you want to be an optimist. So you're saying, okay, I want to know the probability of 2 hearts being drawn without replacement. I'm going to assume that whatever needed to happen on the first draw happened so that I could get the second one as well to satisfy everything. So you're always kind of optimistic with this. And that's why I'm saying here for the first one, we're going to get a heart. And then the probability of the second one, given that the first one was a heart. So now as we start looking at the numbers, there are 13 hearts in a deck of cards. So the probability of the first heart would be 13 over 52. So that's this one right here. Now on the second one, I know I'm not putting the card back. So I've got 51 cards only. And 12 of them that are left are going to be hearts, because in theory I took 1 heart out and set it to the side. So this is, accounting for first card being a heart and being set aside. And more importantly, think of it like not replaced. And that's a terrible looking heart. There we go. That's the way you got to think about it, when you're doing these in succession like this. So then coming to the answer here, you can do some reducing all over the place. So 13 goes into 52 4 times, and it'll go into itself 1 time. 3 will go into 12 4 times, and into 51 17 times. Sorry. And then the 4s will actually go away. So you end up here with an answer of just 1 over 17. And if you need to use a calculator to do that, that's fine. But sometimes doing it that way is quicker for me. So 1 over 17 would be the answer. And this is pretty much the end of this section. There's not a whole lot to this. These three examples are indicative of the type of things I want you to be able to do. But again, the key to these is always remembering it's going to reduce your sample space in some way when you have that given condition. That's what we saw in the last problem here, where the sample space went from 52 to 51 after that first card was drawn and not replaced. Here we took out everything that was aged 35 or less, and then even on the first one we took out all the even numbers. So conditional probabilities always have that sort of aspect to them where you'll limit the sample space. All right, if you have questions, please ask.